Okay. Welcome, everyone. My name is Tomasz Pęczek. I'm very happy to be here today to have a chance to talk to you about architecture and practices for real-time web applications based on ASP.NET Core. There will be some code showing up on screen during this presentation, and Dennis has already concluded in a very scientific way that most of you seems to be managers, architects, so you may not care about the code. So if you don't worry. It's just a background for me to highlight some things for you. If you truly do, then at the end, I will share a link with you and you can find all the code in this presentation. This is also not my only talk about real-time web applications and ASP.NET Core. I have a second one, a more low-level one. It can be considered a prequel to this one. You can find it on YouTube. And in that talk, I go to low-level technical details on some of the real-time technology we, as ASP.NET Core developers, have available. WebSockets, server send events, signaler, and web push. In this talk, I want to show you how on top of those technologies and webhooks, they are also very popular, important in this space, you can build an opinionated initial version of your real-time web application and how you can later evolve that application to address the potential issues that you will most likely encounter. But before I go there, I want to quickly go through the key highlights of all those technologies, because it's quite possible that you didn't encounter all of them in your development life so far. So WebSockets, probably the most well-known real-time technology of the web. All major browsers support it, all relevant server-side stacks implemented. It works by establishing an HTTP connection between the client and the server, and later upgrading that connection into a WebSocket connection. That means a binary connection over TCP/IP, where both client and server can exchange binary messages at any given point of time. So it's extremely powerful, right? Both sides can communicate. The format is binary. You can send everything. The price for that power is complexity. That low-level binary nature of WebSockets is usually visible in the APIs. So you need to put a little bit more effort if you want to create your business logic on top of pure WebSockets. Server send events. A little bit lesser known than WebSockets, in my opinion, mostly because it wasn't supported by all major browsers for a very long time. Now we have a Chromium-based Edge, so it will be supported, as many other things. Go Microsoft. And because of that, it will probably gain popularity. Server send events has a little bit less capabilities than WebSockets, because it's entirely based on HTTP. Client establishes a connection with the server, and that connection stays open. That means only the server can send messages back to the client. And those messages have to be text-based. That's the nature of HTTP. I mean, you can send something binary, but you will have to either base64 encode it or do some other trick. But for price of those limitations, what you are being given is the most performant real-time transport of the web. This is why server send events are gaining popularity mostly in IoT space. There, the communication is usually one direction, and there is a lot of short, simple messages to be sent. Signaler, the go-to choice for ASP.NET Core developers. If you don't know how to start with real-time in ASP.NET Core, you go to Signaler. If you don't end up having any specific business or technical needs, you will probably stay with Signaler. Signaler is a very high-level abstraction on top of those other technologies that I have already mentioned. In most cases, you will end up using WebSockets under the hood. If you are in some weird scenarios, you may end up using server send events and post requests. And if you are dealing with a really legacy browser, think like big corporation exchanging the IT infrastructure every 15 years or something, then you will be using long pooling and post requests. And that's a very bad scenario, so if you have a client like that, be aware, don't use Signaler, preferably not work for this client. Webhooks, a very simple technology. Dennis already mentioned it. It allows you to create a subscription with your server, provide an URL as part of the subscription, and later, whenever you want to notify about something, you just make a request under that subscription. Simple, very powerful. Web push. I know. We all hate web push, right? You open a web page those days, and the first thing you see is a pop-up. Do you want to accept notifications? No, go away. Web push is extremely abused, overused those days. But it's very powerful. It has completely different architecture than all those other technologies. There is additional service in here, the push service. And push service is something which is managed by the browser vendor. It does all the heavy lifting for you. The client creates a subscription with the push service, shares part of that subscription with our server, and whenever we want to notify client about something, we make a request to the push service. Push service is responsible for upholding the connection with the client, notifying the client. It may have additional capabilities, like, for example, waiting till the client comes back online. So these are very powerful features. If you build in your application a proper flow around enabling notifications, show users that there is a value in them, you may gain from this. Just don't be too aggressive with it. So if we take a step back and look at all those technologies at once, we will notice that they can generally be split into two groups. One is the technologies based on having a persistent connection between the client and the server. WebSocket, server send event, signaler. The second is subscription-based technologies. Webhooks, web push. No permanent connection, only a subscription. We are the initiator of the communication. And you probably already expect that this split will be the primary driver of the initial architecture of your application. In case of the connection-based technologies, the entry point to that real-time part of your application is usually some form of a middleware. That's because all those technologies, they have very special, sophisticated technical handshakes that needs to be satisfied in order to establish that real-time connection. So the middleware is a perfect place to do that. When middleware does that, then it can abstract that connected client, pass it to some form of a service in form of a client, connection, other abstraction. That service will be what you will share around in your application to give the business context, access to all the connected users, send messages, sometimes receive messages, list users. And if you've been paying attention, you know I have put Signaler in this group, right? And whoever has been working with Signaler, who's been working with Signaler here? Is it how Signaler looks like? Well, not at the first sight, but generally, yes. Under the hood of that very sophisticated abstraction, there are middlewares, Lambda middlewares, which are performing all the kinds of handshake for either the WebSockets or the server send events. There is the service, that's the hub context. And there is that additional things, which are hubs, which are simply yet another abstraction to enable you to work with connectivity events and receiving messages easier. But generally, it's still the same thing. When it comes to the subscription-based technologies, the entry point is usually some form of a controller or other API. The goal is to give your users capability to manage subscriptions. That's the key part. They need to be able to create them, edit them, remove them. That means we need some storage. Only on top of that, we can expose some form of an API client, which will be dealing with, once again, allowing other parts of our system, our business context, to send messages to the connected clients. Now, those two initial architectures, they are quite different, but they share one important thing, the one which is either represented by that service or that API client, sending. Sending is the most important concept when it comes to real-time web applications. In some cases, through that real-time channel, you can receive, that's WebSockets, that's Signaler, but usually receiving is not the main feature of your real-time part. Usually receiving becomes just another entry point in your application. And with all the problems you have with receiving, you can deal the same way. You are dealing with problem with receiving HTTP requests, other things. If it happens that receiving is extremely important in your application through that real-time channel, all the patterns I will discuss here for sending can also be applied to receiving. But sending is usually what you care the most about. And it's usually when all the problems appear. So what you want is the ability to evolve your sending code over the time. You never want to expose the actual technology under the hood to the business part of your context. So you need some simple abstraction, something which represents that sending as a logical operation. You put the actual technologies, server send events, WebSockets, signaler, webhooks, web push, with that subscription management, you pull it under that very simple interface. And actually, the implementation of that abstraction is usually very similar. It's important to remember, the goal is not to be able to replace one implementation with another. Many times when people are talking about abstractions, they will tell you, yeah, because you want to exchange that data access layer with something different. That usually doesn't happen in real life. In this case, it actually doesn't have any point. I mean, you wouldn't exchange connection-based technology with a subscription-based one. Doesn't make sense. You wouldn't exchange webhooks with web push. Completely different business scenarios. You may end up, in some cases, exchanging signaler with WebSockets, with server send events, if you have really specific business needs, really specific performance needs. But most of the time, that's not the case. You want to be able to evolve that code to solve the problems you will appear. Because if you create your initial application, if it has some business value, if it marketed properly, the users will come, and users using your application are the primary problem with the software, right? If there will be no users, you would have no problems with the software. But for some crazy reason, we want users to use our software, so we are starting having problems. And the first problem you are likely to encounter is a lot to send. That means there is a lot happening in your application, for whatever might be the reason. Maybe users are doing something, hopefully, and you have to notify other users about it. Or maybe you simply have a spanning marketing company and you're sending a lot of stuff. If that's your thing, okay. But the problem is here from the technical perspective. For the connection-based technologies, you can only push a signal message at once through that real-time pipe in one direction. Once you start sending a message, you must finish sending the message before you can send another one. That means if you have a lot to send, you will start seeing delays. Messages will be waiting to be sent out. And if you have implemented your application, as most of the people do when they start working with the code, that sending happens in context of your business process. So that's a delay to your business process. If you have implemented your application in the way it often happens, that business process might be executed in context of your request response. So that's a delay to your response time. In general, that will reflect poorly on your application performance. And you don't want that. You want to decouple that sending logic from the actual business process. Now, you might think that the problem is not there for the subscription-based technologies, right? After all, in theory, you can make as many parallel requests as you want to that server over there, right? Well, that's the theory. The real life is different. That server, on the other end, is a real server. It has limits, and you're probably not the only one hitting it. So at some point, it will throttle you. It will give you an error response saying, you have to wait. This is, again, a delay that you have to calculate into your business process, that you want to decouple from your business process. And in many occasions, when people are faced with this problem, they choose fire and forget as their solution. Well, the logic is simple. If I can forget about doing something, I don't have to wait for it, right? Problem solved. But this is a trap, because you are losing power, you are losing control, and creating good software is all about control. If you will have any new requirements for that real-time part, for example, you want to have a different retries, and you depend on order, or you want to do some dead lettering stuff, you no longer have a place to do it. There are better patterns in software development than fire and forget to deal with the problem of a highly active producer and not fast enough consumer. I'm talking about queues. Queues are one of the standard solutions for this kind of problem. So we can introduce queues into the real-time part of our application to lessen the load on the actual technology we are using. In case of a connection-based technologies, we can put that in front of our service. In case of subscription-based technologies, you can put that in front of our API client. But that, again, is a trap. When I'm saying queue, what is the first thing that comes to your mind? I think I heard rabbits somewhere over there. Probably somebody said Azure Queues or something. This isn't the right choice, at least not if you really have to. Those are separate services. They are outside of your application. They are boundaries you need to cross. And boundaries, when we are talking about real time, are very expensive. They are taking the important milliseconds, microseconds, or even seconds that you want to use to deliver your message. So your first thought when you are introducing something and you are creating a real-time web application should be, I want to stay in memory as long as possible. So the first type of queue you should try to introduce is an in-memory queue. For many cases, that will be good enough. Of course, it's not as powerful as a queue as a separate service. No persistent messages, etc., etc. If you happen to be in a situation when you need those capabilities, or you really have such a big load that in-memory queue can handle it, then you can go outside to a separate service. But remember, you are paying with latency. Delivering your messages will take longer. But once you introduce queue, either that in-memory queue or a separate service, what you can do is change your sending abstraction. That was the purpose of it. And instead of actual performing the send operation there, you can enqueue a message. That should be fast, reliable. That will decouple the business code from the actual technology causing performance problems. Of course, any solution in software doesn't come for free. And the price we usually pay, at least in the first step, is more complexity in our software. This also happens here. That new complexity is coming in form of a dequeuer. That's a new service, something which is constantly there running in the background of our application. It takes all the new requirements, so it's looking at the queue, checking if there are new messages. If you want to add retries, they go here. If you want to add some dead lettering stuff, it goes here. It also has to handle the pre-existing technology for sending the messages. In case of the subscription-based technologies, it can even get more complicated. That previous service could have any scoping we wanted. The queuer has to be a singleton, because in context of ASP.NET Core, it has to be a hosted service. That's a way to run something constantly in the background. And because we are dealing with subscriptions, because we are dealing with storage, some drivers for storage, they don't like to be used in context of a singleton. Entity Framework is a shining example. Try having a DB context alive for the entire lifetime of your application. I dare you. See what happens. So you need to be aware that you are changing things, more complexity is coming. You need to work with that complexity, you need to address it, you need to solve it. Once you will solve it, you will probably solve a lot to send problem. That will mean more users will be able to come to your software, more users will be able to use your software. That means those users will cause more problems with your software. After all, users are the reason of the problems with the software. So the next problem you are most likely to have is a lot of clients. That's a nice problem to have, right? After all, at some point, it was our goal. Now we generally probably like, why those people are using my application? Why is it crashing? Well, it's crashing because in context of real-time technologies, users mean resources. For the connection-based technologies, every user connected to our application means a persistent connection, means some socket utilization, CPU utilization, memory. Those are limited. A single instance can handle only this much. For the subscription-based technologies, the problem is the storage. Well, maybe not the storage itself, it's pretty cheap those days, but accessing the storage, that's a completely different story. If you have millions of subscriptions, finding a one quickly can be challenging. Doing a broadcast to all of them, that's an interesting story. How long it will take to start from the first subscription and end with the last one. We want this to be performant. And code tricks, any kind of optimizations, can take us only that far when it comes to those problems. At some point, we will have to scale out. Those days, luckily, we know how to scale out, right? We take a container, we choose our cloud hosting, and we build a Kubernetes cluster. After all, for many people, that's what the cloud truly is. Our containers on somebody else's Kubernetes cluster. Never create your own Kubernetes cluster. Does this solve the problem? Well, For the connection-based technology, it depends. It strongly depends on how your application is behaving. If the reason to send a notification always happens on the same instance that the client is connected to, okay, and you are not doing broadcasts, because that will not work. Usually, at least one of those two conditions is not met. What you need in this case is some form of synchronization, something which in terms of real-time web applications is usually called a backplane. That's a boundary you will have to cross to synchronize between all the instances which you currently have in production. And there are established patterns to do so. One very simple one is usually based on Redis. That's because Redis is easy to get in every cloud, is cheap, quite performant. It has a very nice publisher-subscriber implementation. That's what we care about. We want that publisher-subscriber implementation. We want to, once again, change our sending abstraction to, instead of a sending, perform a publish operation into a Redis channel. At the same time, we want to subscribe into the Redis channel, and whatever we receive, we want to push in our internal queue. Hopefully, this time, this can really be an in-memory queue, because if we have to use both Redis, queue as a separate service, then we are not real-time anymore. So as less boundaries as possible. Of course, Redis is not the only option here. You can choose any publisher subscriber which is available in your infrastructure, if it is simply performant enough. Will this solve the problem? Well, yes. The problem is no longer there. Is it the best solution? Well, now is the part for all the architects, managers here in the audience, which are the majority. That depends on your team. As Dennis said, having a Kubernetes cluster, that requires a skill set. It's not easy to do. There are different options if you are not focused about being cloud agnostic. If you don't care about vendor lock-in, then you can choose a specific cloud and easier to use services which that cloud offers. For example, for ASP.NET Core, one of typical choices is Azure, right? And Azure has different services which provides this capability. For example, App Service. App Service has an auto-scaling plan. It's a lot easier to use than Kubernetes cluster. So if your team doesn't have the skill set, you can go this path. I can actually see in situations when App Service plan were most cost-effective, managers, that's the moment for you, most cost-effective when it comes to money than running a Kubernetes cluster. So always consider your options. If you are using SignalR, you can consider Azure SignalR services. You can think of it as your SignalR stuff running into auto-scaling plan with some kind of a backplane, or wrap it in a box exposed through APIs. Ready to use, just pay with the money. But it might be the greatest options if you don't want to invest in other parts of your software. Now, coming back to that Kubernetes cluster, and coming back to the subscription-based technologies, because I haven't spoken anything about them yet. Does the cluster solve the problem there? Well, the problem in this case was the storage, or more likely, accessing the storage. Does the cluster help? Not a lot. I mean, if we are doing broadcast, still, a single instance has to go through all the subscriptions which are in the storage. That's still not performant. That still takes a lot of time. That's not how we want the things to work. Of course, it will be a little bit better because other instances can do other work in this time, but generally, it sucks. So we once again want to change our sending abstraction, and we want to introduce sharding when it comes to managing these subscriptions. Sharding is about horizontal partitioning of our data. We can do it in several ways. We can do it within a single database into multiple tables. If we want to care about geolocation, having the data closer to our clients, then you can spread into multiple databases, have those databases closer to our clients. That's the technical layer of sharding. There is also the logical layer that we need to take care of. There are two general strategies in which you can implement sharding. Either you have a very specific key and an algorithm which is able to define a shard very quickly based on that key, or you have some kind of a value which nicely falls into ranges, and you can build shards based on ranges. For the subscriptions, in case of a real-time technologies, ranges are usually the good primary choice. You can go for the simplest range possible, which is the index of your subscription. You simply measure how many subscriptions can my instance handle in case of a broadcast or other scenario. Let's say it's 10,000, I'm guessing that number. So if that's the number, then you want your shards to be a size of 10,000. And that's that new complexity that you have to pay with for solving the problem. That controller, that API you had for managing subscriptions, now needs to be able to handle sharding. It needs to be able to split your data, create new shards when necessary, fill the shards which have gaps, because somebody could have removed subscription. You have to handle all of this. If you do it, then every instance will be dealing with the equal size of data, it will be performant. At the same time, you probably still want to have a key-based capabilities, because if you are sending to a specific client, then you need to be able to quickly identify the shard that this client belongs to. If you keep that index with your basic client information, it's good enough. You will be able to find the shard quickly, so it will work. Is this the best solution? Well, it depends, right? Dennis has been telling a lot, it depends. I'm telling a lot, it depends, but that's the truth. I will tell you on what it depends. It depends on what your application is doing. If the primary concern of your application are broadcasts, then yes, this is a perfect approach. All instances are constantly sending to all the subscriptions within their corresponding shards. Everything is utilized, nice. Once the balance starts to shift towards sending to single clients, it's getting less and less effective. Because that means you have a lot of unutilized resources. If you are dreaming about quickly scaling up, spawning new instances when you are about to do a broadcast, stop. It won't work. It won't scale. It will take a lot of time. So if you are doing messages to single clients, you are paying, managers, pay attention, you are paying for unutilized resources. You are basically burning money. You don't want that. So if you are in this situation, you probably want to achieve a holy grail of auto-scaling when it comes to that subscription-based technologies. Is this possible? Well, let's rethink our requirements. We have a very simple logic. You are making a request to an endpoint. For a webhooks, just plain HTTP request. For web push, well, there's some encryption, very sophisticated authentication, just still a request. It's stateless. There is no state. It needs access to storage. Okay. It needs to be able to react to some form of an event, trigger, for example, something from a queue. If you look at this from this perspective, and the capabilities that those days technologies, those days clouds give you, you may come up with this idea. Serverless, Azure Functions. They seem to fit all the requirements. It is perfectly possible to implement an Azure function which will deal with sending the notifications. This is a simple implementation for web push. Does it solve the problem? No. Why? It is dealing with all the subscriptions inside. And I already said, this will not be performant. If I'm supposed to go through the entire storage of the subscriptions, that will take a lot of time. I wouldn't like to be at the end of that list. So, this is a good idea, but it needs improvement. Luckily, those days, we have ways to build very powerful things with serverless, especially if we are talking about Azure Functions. Because Azure Functions have durable functions, a way to create workflows in a serverless way. And we can use one of the very common patterns for durable functions to address this problem. Fan out. That initial function can focus only on receiving the trigger, receiving the message from the queue, grabbing information about all the available shards, and spinning new functions. Every one of those new functions, they will only deal with subscriptions within a specific shard, which will be performant, fast enough, because we have measured decided how big the shard should be, it will work. It will scale nicely. That's what Azure Functions has been designed for, to spin those functions very quickly for you. Handling sending to a specific client in this approach is also very easy. You either have a completely separate function that deals with specific clients, or you route that through that initial function. So it's clean, it's separated. It will nicely scale for both of the scenarios. So if serverless is such a nice solution when it comes to auto-scaling for the subscription-based real-time technologies, can we use serverless for the connection-based technologies? If you're using Signaler, you may have an option, because that Azure Signaler services, it has ready-to-use connectors for Azure Functions. If you are using WebSockets, servers and events, don't try, because Azure Functions is not able to directly work with those technologies, so you would have to essentially rebuild Azure Signaler services on top of their WebSockets or servers and use directly. If you are creating all this infrastructure of the services, you already have a place to deal with receiving triggers, sending the messages. You don't need Azure Functions. You shouldn't introduce Azure Functions into your system just because they are cool, just because they are out there, because that's necessary cost. Also, in this case, when you are using Signaler, you should be cautious not to introduce Azure Functions only as a router. If you have some different piece of infrastructure that is close to that and can deal with the routing, stay with that. On many occasions when I have seen Azure Functions being introduced just as a router, and I asked the question why, the answer I was given is because it gives you real-time data observability. The magic of Cosmos DB trigger, right? We can create a function, apply Cosmos DB trigger, somehow it always runs when data changes. That's cool. But you are not limited to Azure Functions to achieve that. You can use change feeds or change streams, the name differs based on the technology, directly in your application. If you choose that path, you are not limited to Cosmos DB. Well, maybe limited is not the right word, right? Because Cosmos DB is a great database, very powerful, great features. It simply might not always be the right choice for your scenario. If you go a path of your own implementation, you have options. MongoDB, RefingDB, Raven. There are more technologies with change feeds. More are coming. Blob storage is supposed to get change feeds, because change feeds are very important. Real-time data observability is a trend that all the services want to expose. And those days, thanks to C#8, we have a very nice way of representing change feeds in our application, async enumerables. We can nicely hide the technology under the hood. This is a high-level implementation for Cosmos DB. There is a lot of complexity hiding under those methods. Cosmos DB actually has the hardest path to implement the change feed by yourself. If you don't want to deal with the partition, key ranges, etc., you can use a change feed processor, which is there for Cosmos DB. It solves those problems. It's introducing different problems because it's strongly pushing you toward producer-consumer pattern. But you can do it. For MongoDB, it's actually simpler. Not so much hidden complexity. For RefingDB, it's like magic. Right? Well, RefingDB is an interesting option. It was a quite popular database some time ago. Not those days. Those days, I wouldn't suggest you use it for production. Although the current team responsible for it, they are claiming they are getting back to speed. It will be updated, it will be maintained. Hopefully, that's the truth, because it was great database. I like to see it back again. Those days, what I would say you should use RefingDB for is proof of concepts. Because it's extremely simple to deploy it, either in container or locally. Write those couple lines of code. You can test your assumptions. You can test your architecture. Once your application grows, then you can switch to Mongo, Cosmos, whatever, right? You have a nice API. You can replace the implementation. One of the first time when actually abstraction is for replacing the implementation. So this is there. Don't go the default path. Don't choose the default services. Always measure, calculate your costs, calculate your knowledge, choose the right tool for the job. Now, For the last part of this talk, I want to go a little bit beyond the web. Because that's what ASP.NET Core did with the 3.0. They have introduced new capabilities in the real-time space, which are actually targeted not for pure web, but more for service-to-service scenarios. You probably already know that I'm talking about gRPC, right? gRPC is a new hotness in the ASP.NET Core world, which is kind of surprising because gRPC has been there for a very long time. It has been created by Google on top of HTTP2 and protocol buffers, and there was a .NET implementation in there. It was providing all the capabilities, so all the interactions, request response, streaming, etc., etc. But people were not using it so frequently when it comes to .NET world. In Java, yes. C++, yes. .NET, not so much. Why? Because .NET developers are lazy. And that's a good thing. It's good to be a lazy developer because it means you are looking for a good solution, the right solution. .NET developers, they want good tooling. And tooling in context of gRPC is extremely important because the primary thing you work with when it comes to gRPC is a protofile. gRPC is schema-driven. You define your services, their methods, the types they are using in the protofile. Later, you need to synchronize your code with that. The protofile is what you share with your clients, with other team members, so they can generate client code from it pretty quickly. And that wasn't possible with the tooling provided by Google. What Microsoft did with ASP.NET Core 3, they first of all re-implemented gRPC. It's now completely native .NET code. The previous implementation from Google, it depended on some C++ libraries, so the cross-platform story wasn't that good, etc. We have a new implementation, fully managed one, and we have a great tooling in Visual Studio. We can be lazy. We can write the protofile, click, right-click publish, sorry, wrong button, click run, and you will be given this. Nicely scaffolded classes waiting only for your business logic. That's the development story we want. We want to focus on the logic. So gRPC is very hot right now in ASP.NET Core, in generally in .NET Core space, because we can build a very performant services on top of it. And I keep saying it's for services. It's not for web. Well, you might have heard about gRPC Web. Let's be honest, that's a workaround. gRPC Web, in its specification, assumes a presence of a proxy. In its reference implementation, that proxy is an envoy. Why? Because browsers are not capable of doing gRPC correctly. The way gRPC is using HTTP2 and protocol buffers is not possible to implement in browsers. They don't have those capabilities. So there is a limited version of gRPC that the browser can speak. It speaks that limited version of gRPC to the proxy, and the proxy speaks with the actual gRPC service, which is speaking full gRPC. Now, you probably already know that this is not performant. There are two boundaries you have to cross. One is between the browser and the proxy. The other is between the proxy and the service. And that protocol between the browser and the proxy is not performant enough. So gRPC Web is something you can use. Actually, ASP.NET Core will have an implementation of that, which probably will be a little bit better, because probably the proxy will not be a separate service, which is a good thing. But it still won't be as performant. You should use it only if you really have to reuse your gRPC service in a browser scenario. If you are building something intended for the browser from the start, focus on Signaler or something else. gRPC is not for that. This is as far as I will go when it comes to gRPC in this talk. There are other talks devoted completely to gRPC. Personally, I recommend the one by Mark Gravel from Stack Overflow. You can find it on YouTube. Go there. There's one more thing I wanted to show you in this talk. WebSockets. WebSockets is also something which might be coming to .NET, to ASP.NET Core developers. It's very popular technology when it comes to Java space. It's a real-time technology based on persistent connection. That connection can be the TCP/IP, Aaron, or WebSockets. It's strongly driven by reactive manifesto. That means performant, bidirectional messaging, parallel messaging. That means all the typical interactions, fire and forget, request response streaming. One very unique interaction called channel. Client can open a channel with the service. The service at this point is sending the entire state of the world communication back to the channel. And from that point in time, only deltas are being sent whenever data are changing. Server is reacting to that, sending delta. Client is reacting to delta. A fully reactive model of communication. And why WebSocket is becoming possible in ASP.NET Core? Because with ASP.NET Core, we have been given a low-level network primitives for the web. What you can do now, and you can use it in many scenarios, is grab a worker template, drop bare Kestrel into it. That will give you all that performance that ASP.NET Core has. It will deal with all hard-to-do network stuff. Managing connections, reading, writing. What you will be given is some connectivity events and a pipeline-based API for reading and writing. And it so happens that the initial implementation of WebSocket for .NET is based on pipeline APIs. So building a very simple WebSocket service is fast and easy. This is not for production. WebSocket, when it comes to its .NET implementation, is very immature. There is a lot of open questions, how the project will evolve, how it will grow. Will we be given a higher level APIs for the server? Now, it's a nice experiment. You can take a look at it, see how it plays for your workflows. You may be able to use that in the future. Those are the links I promised you in the beginning. The first one is to my blog. I write there a lot about real-time architecture, real-time technologies, and a number of different things. The second is to my GitHub. All the code in this presentation is there in one form or another. There are demos for WebSocket, server send events, web push, WebSocket, change feeds. Go get them, grab them, use them as you need them, build great real-time web applications. Now I'm guessing we are switching for questions, if we have internet. Okay. Can we use GRPC in Azure? We should be, soon. App Service is supposed to be given support for GRPC, to expose GRPC services through the App Service. If you are using Kubernetes in Azure as a cluster, then yeah, you can deploy there your container, it will work. There is a long-running client-side task like playing a video. The client needs to report the server its real-time progress. What would you use to implement that? Well, the simplest approach, SignalR, preferably with the queue under the hood. The important part is implementing the process which represents that long-running task. That process needs to be able to report somewhere, preferably not directly to the client. A fast queue, maybe a in-memory queue, or a persistent queue in that case, because reporting progress doesn't have to be that real-time. So if we have a queue in which that process is reporting back the progress, we can have a SignalR service in a simple case listening to that queue, or we have an Azure Functions with SignalR services listening to that queue, pushing the progress back to the connected client. What is the other reason for using abstractions, except reflecting the implementations? There are two reasons. First is to not depend on the direct implementation. That's for testing. The second is to be able to, what I was mostly doing through this entire talk, to be able to decouple the changes in the code from the entire rest part of your software. So you're usually not replacing the implementation. That actually happens very rare, only in your proof of concept on something. What you usually do is you evolve the code under the abstraction. You give it more capabilities. You are introducing separate technologies. But usually the core stays the same. It's simply to give you freedom. It's to decouple one part from the another. Okay. From the top, I'm guessing. What is the boundary between classic Web API and real-time data transfer? When do you switch from Web API to real-time? That's a loaded question. That's primary business-driven. That depends what your business expects from you. Also, that depends strongly on the initiator of the communication. Web APIs are always initiated by the clients generally, right? Client needs to make a request to get the data. Real-time technologies, they give us that power of us initiating the communication back to the client. The other thing is simply how fast the business wants us to push those messages to the clients. If it's fine when clients comes next time to the page or refreshes the page for whatever reason, then Web APIs are a lot better. They are simpler. They are less expensive when it comes to resources. If the clients needs to be notified immediately for whatever the reason is, either the monitoring or the engagement, then that calls for a real-time technology. Okay, I'm guessing that's all of the questions, right? If you have any other questions, I'll be here for the entire day. You can grab me as part of the hallway track, or I probably will be in the speaker lounge if I'm not in the hallway or somewhere there. Find me, have a chat with me. I'm very happy to. Thank you.